Okay, so today we are continuing our topics on general relativity. Last week we did a bunch of like tensor math and stuff, but I think it probably wasn't very practical to learn a bunch of that stuff in like 30 minutes. Kind of a lost cause, so I cut down on the math today, so because of that it's going to be pretty short. But today we're doing the Einstein field equations, Christoffel symbols, and the geodesic equation. Okay, so first, last week we mostly talked about like how tensors work and stuff, but we also talked about important tensors that we use. One of them is the metric tensor, which is an object that tells us how to measure direct distances in space-time. This works kind of like a ruler. The Riemann tensor, which is an object that tells you about the curvature of a space. And the stress energy tensor, which is an object that describes physical quantities like pressure and energy and stress and momentum of matter. Another thing is that we will see a lot of partial derivatives today. So last week I briefly said what a derivative is. It's basically just tells you a function's rate of change or slope at a specific point. And partial derivatives work the same way, but they are used with functions of multiple variables. So for example, we have this function f of x and y is 2x plus 3y. So the partial derivative with respect to x of f of x comma y is just going to be 2. We ignore the y term, and just the slope of 2x is 2. So the partial derivative with respect to x is 2. And same process for partial derivative with respect to y. It's just we ignore the x term and we get 3. So basically whenever you see the partial derivative, it still means the same thing as a regular derivative, just rate of change. Okay, so first thing is the Einstein field equations. So the Einstein field equations tell us how the curvature of spacetime reacts to the presence of energy and momentum, quote by Carrol. So this is the general Einstein field equation, where we see r mu nu is the Riemann tensor, which describes curvature. R is what's called the Ricci scalar, which is basically just a number that is derived from the Riemann tensor. It also talks about curvature. G mu nu is the metric, which we said tells you how to measure distances in a space-time. G is just the regular Newton's universal gravitational constant, and T mu nu is the stress energy tensor. So the left side of the equation with the Riemann tensor and the Ricci scalar and the metric, that is telling you about curvature. And the right side of the equation with the stress energy tensor is telling you about matter, which is what the quote from Carrol said. It tells us how the curvature of space-time interacts with the presence of matter. Okay, so that was just like the general Einstein field equation, but like depending on the situation, we might like edit it a little bit. One example is if we're working in an expanding universe. So unless we're specifically working in a model that takes universal expansion into account, we use the previous equation. But when we are talking about universal expansion, this is the Einstein equation we use, where it's just the same thing, except on the left side of the equation there's a new term, lambda g mu nu, where lambda is the cosmological constant, which tells you that the vacuum of space has an intrinsic energy density. And we saw lambda a couple weeks ago when we were talking about like the expanding universe and stuff. Another variation of the Einstein equation is in a vacuum. Of course, where the universe isn't expanding. In a vacuum, there is no matter and there is no energy. So the stress energy tensor T mu nu vanishes, or goes to 0, and so we get this equation. So yeah, that is pretty much it for the Einstein field equations. They relate the curvature of space-time to matter and energy, and then we saw a couple different examples of like variations of the equation, where in an expanding universe it includes lambda, the cosmological constant, or in a vacuum where the stress energy tensor vanishes. Okay, so moving on to Christoffel symbols and geodesics. So the motivation for this topic is that naturally particles, when they're just like traveling through space, will take the path of least resistance, which is just going to be like the shortest straight path. But when we're working in curved space, it's hard to tell what that path, called the geodesic, is going to look like. So we use the geodesic equation to tell us what that straight line is going to be. And in the geodesic equation are these things called Christoffel symbols, so we're going to define those now. So, another quote from John Carroll from his book on general relativity is he said that all the ways in which curvature manifests itself rely on something called a connection, which gives us a way of relating vectors in the tangent spaces of nearby points. There is a unique connection that we can construct from the metric, and it is encapsulated in an object called the Christoffel symbol. So, you can we don't really care about all that garbage about tangent spaces, nearby points, whatever. Basically, because we said that we're not going to pay attention to the math all that much this time. So basically the Christoffel symbol, it is denoted by that, it looks like an upside down L. It's in uppercase gamma, and it just tells you about curvature. It's just another object that is describing curvature. So yeah. So now that we know what the Christoffel symbol is, we can take another look at the Riemann tensor. So we said that it is the technical expression of curvature, so naturally it is going to include Christoffel symbols. And so we can see that in that definition there. How else are Christoffel symbols used? Christoffel symbols are used in the covariant derivative, which is denoted by that upside down triangle called nabla. And that covariant derivative is just a generalization of the partial derivative. As you can see in that definition, the covariant derivative of a vector is just going to be the partial derivative of the vector plus the Christoffel symbol term. And the reason for this is that the partial derivative doesn't work well with tensors in curved space, so we have the covariant derivative. And Christoffel symbols are also used in the geodesic equation. So moving on to geodesics now, we have this concept of parallel transport, which is moving a vector along a path while keeping it constant. So when a vector is parallel transported, the covariant derivative of the tensor vanishes. And this makes sense, because what it means by the covariant derivative of the tensor vanishes is just the derivative is 0. The derivative is the rate of change, so it's not changing. And that's exactly what we said parallel transport is, moving a vector along a path while keeping it constant. So, yeah. And so a geodesic is a curve along which the tangent vector, the vector parallel to the path, is parallel transported. Or more intuitively, if you walked along a geodesic, you would just be walking forwards. And another misconception is that a geodesic is not necessarily the shortest path between 2 points. If you have a sphere and you're going along the equator, I guess, you could go either direction to get from one point on the equator to another, and it would still be a geodesic because it's still a straight path, even though one way might be shorter than the other. So yeah, a geodesic is not necessarily the shortest path, but just a straight path. So when we figure out what a geodesic is, it's pretty easy to see in flat space. It's just a straight line. But in curved space, it's more difficult. And so we see we've got that map of straight lines on Earth, which is obviously a sphere, it's curved surface. So you can see that it's kind of hard to tell what the geodesic is going to be between 2 points. And so to help us figure out what that's going to be, we have the geodesic equation. And so what you do is you just kind of input the vectors and all the information for the Christoffel symbol into it, and you get out the formula, I guess, for the line for the geodesic. So how are geodesic equations used? So one example of where we use it is understanding the properties of gravitational fields of stars. So since stars are massive objects that bend space-time, they create curved space. And when photons from other stars, for example, are approaching the gravitational field, they bend around the star, following a geodesic. Yeah. And then so we've just got these 2 videos here which just give a longer explanation into the intuition behind a geodesic and the mathematical reasoning and stuff. And the second video gives a couple examples so you can better see how the actual equation is worked out and used if you want to watch those. I guess I will include a link to the presentation so you can get these links. Okay, so that's pretty much it. Quick summary of Christoffel symbols in geodesics. So we use Christoffel symbols when we talk about curvature, like in covariant derivatives, the Riemann tensor, and the geodesic equation. And a geodesic equation is just a straight line. And the geodesic equation tells us what that line is between 2 points. Yeah, okay, so that is pretty much it for today. I guess I'll just like upload this on YouTube or something. I don't even know, but yeah. Okay, so thanks guys. See you next week. Bye bye.